A star dies in a cataclysmic supernova, vanishing into a black hole. But what if that is not the end of the story, but a cosmic beginning? Tonight, we explore a theory so profound it redefines reality itself. The idea is that certain stars, known as Singularity Children, do not simply die. Instead, they give birth. Their final collapse may spawn entirely new universes, separate realms of space and time with their own laws of physics. By the end, you will understand one of the most radical possibilities for the origin of everything. We will investigate how a singularity could become a portal and ask what strange signal might be the birth cry of a new cosmos. What does it mean for our own universe to have stellar parents? The mystery begins with a single, terrifying point. At the very core of a black hole, crushed beneath the weight of a dead star, lies a gravitational singularity. This is not a place you can visit or a thing you can touch. It is a mathematical boundary, a point of infinite density where all the star's mass has been compressed into a volume of zero. Space and time, as we understand them, cease to exist here. The equations of Einstein's general relativity, which so elegantly describe the warping of the cosmos, produce results that are nonsensical at this point. They scream infinity, a sign that our physics has reached its absolute limit. This singularity is the ultimate end of the line for our universe's rules. It is the final period in the sentence of a star's life, or so we thought. But there is another famous singularity in our cosmic history, one that represents not an end but a beginning. The Big Bang itself is thought to have emerged from a similar state of infinite density, a cosmological singularity from which all space, time, and matter erupted. So we have two singularities, one that seemingly ends a universe within a black hole, and one that began our entire cosmos. This is the profound puzzle that gives the theory its power. What if these 2 points are not different in kind but in outcome? What if a gravitational singularity is not a dead end but a doorway? The terrifying collapse at the heart of a dying star could, under the right conditions, become a cosmic seed. In this view, the singularity is a bridge, a violent portal that leads not to nothingness but to a new everything. It is the moment of rebirth where the death of one reality becomes the labor pains for another. This shifts our entire perspective. A black hole is no longer just a tomb. It becomes a nursery, and the stars that create them are not just ending their stories, they are potentially becoming parents. This leads us directly to the central characters of this cosmic drama, the special stars destined for this bizarre fate. They are the Singularity Children. The concept of a child universe transforms a black hole from a cosmic drain into something far more creative. To understand how, we must step beyond the known physics of Einstein and into the speculative realm of quantum gravity, where theorists like Lee Smolin and Andre Linde have planted extraordinary seeds. Their work suggests that the singularity at a black hole's heart does not simply sit there, a permanent scar on reality. Instead, it might undergo a process called a quantum bounce. In this scenario, the unimaginable pressure and density reach a breaking point, not for the matter itself, but for the fabric of space-time. The singularity could literally pinch off, like a soap bubble that forms on the side of a larger one, detaching completely to float away on its own. In that moment of detachment, the connection to our universe is severed. The new bubble, born from that pinched-off singularity, becomes its own separate cosmos, a child universe with its own beginning, its own expanding space, and crucially, its own set of physical laws. This is not a far-flung region of our own cosmos. It is an entirely different reality, unreachable and unknowable to us. Think of it like a mighty tree. Our universe is the trunk and the main branches. A black hole singularity is like a dense, twisted knot in the wood. From that knot, under the right conditions, a new branch can sprout, growing in its own direction, with its own pattern of leaves and bark, ultimately becoming a tree in its own right. The child universe may inherit some properties from its parent, the way a branch carries the tree's DNA, but the conditions of its explosive birth could tweak the fundamental constants. Perhaps in that new realm, the force of gravity is slightly stronger, or the speed of light is a different number. These tweaks are the cosmic equivalent of genetic mutations, leading to universes that could be wildly different from our own. This idea leads to a breathtaking possibility, a concept known as cosmological natural selection. If black holes give birth to new universes, and if those universes can, in turn, produce stars that collapse into black holes, then the cosmos itself could be subject to a form of evolution. Universes that are better at making black holes would produce more offspring. Over an unimaginable cascade of generations, the laws of physics we see in our universe, the very laws that allow for stable stars and planets, might not be random. They might be the ones that are exceptionally good at creating more black holes and thus more cosmic children. So when we look at the night sky, we are not just looking at the aftermath of stellar deaths. We might be looking at a forest of cosmic parents, each black hole a silent seed from which an entire new reality has grown. These cosmic parents, the Singularity Children, are stars of almost mythical proportions. They are not the red giants or white dwarfs we commonly find. To birth an entire universe, a star must be something profoundly different. A celestial entity of such extreme mass and exotic composition that its death is not a simple collapse, but a transformation of reality itself. Picture a star so massive it makes the largest black hole we know seem modest. Its core is not just iron, but a soup of even denser, stranger particles, perhaps what physicists call strange matter, a state so stable and dense it defies our normal understanding of atomic nuclei. These stars likely existed in the frantic, dense early chapters of our own universe, when conditions allowed for such monstrous structures to form. Their fate is the key. When a typical massive star exhausts its fuel, its core collapses into a neutron star or a black hole. But for a singularity child, the collapse is different. The pressures and densities at its heart are so unimaginably severe that they do not just crush matter, they crush the very framework of spacetime. Instead of forming a stable event horizon around a permanent singularity, the entire process becomes unstable in a new way. The collapse does not stop at creating a black hole as we know it. It pushes through, triggering that quantum bounce the moment the singularity pinches off and inflates into its own separate expanse. In essence, these stars do not leave behind a corpse in our universe. They perform the ultimate magic trick, vanishing from our reality entirely and leaving behind not a tomb but a womb. Their entire mass and energy become the seed for a new cosmic beginning. So when we look for these progenitors, we are not looking for black holes. We are looking for the absence where one should be, or for a signal that is not a death knell but a birth cry. This radical idea turns our textbook understanding of stellar evolution completely on its head. For over a century, we have mapped the life and death of stars with elegant clarity. A star like our Sun will swell into a red giant, then gently shed its outer layers, leaving a cooling white dwarf. A more massive star will explode as a supernova, its core crushed into a city-sized neutron star. The most massive stars of all collapse completely, vanishing behind the event horizon of a black hole. This has been the established cosmic endgame, a fate determined by mass. But the theory of Singularity Children proposes a hidden fourth path, one so extraordinary it redefines what death even means in the cosmos. In this view, for a special class of primordial stars, that final gravitational collapse is not an ending. It is a beginning. The star does not merely leave a remnant behind in our universe. It uses the very energy of its own destruction to ignite a new reality elsewhere. This is not just star death, it is cosmic reproduction. The star becomes a parent. This challenges the core of stellar astrophysics because it suggests that our universe contains engines of creation we have not yet learned to see. Our current models beautifully describe how stars live and how they leave corpses, but they stop at the singularity, treating it as a full stop. The child universe theory asks us to consider that the period might actually be a comma, followed by a sentence written in the laws of a different reality. It fits into the broader story like a missing chapter, one that explains not just the fate of the star, but a potential origin for everything. If true, it means the stellar life cycle is not a closed loop within one universe. It is an open-ended process that can spawn new cosmic lineages, making stars the architects of a multiverse. The next question becomes urgent and haunting. If these events are happening or have happened, could we ever detect them? Is there a signature, a cosmic footprint that a star has not just died but given birth? The birth of a new universe would not be a quiet event, even if we cannot hear it. To understand the possible mechanics, we must venture to the very edge of what physics can describe, to scales so small they are almost meaningless. This is the Planck scale, a realm where the smooth fabric of spacetime predicted by Einstein dissolves into a seething, chaotic quantum foam. Here, reality itself flickers. Tiny bubbles of space and time can pop into and out of existence spontaneously, a process driven by the inherent uncertainty of the quantum world. Normally, these quantum fluctuations are vanishingly small and short-lived, appearing and disappearing in an instant. But inside the crushing heart of a collapsing singularity child, the rules are anything but normal. The gravitational pressures are so extreme that they could amplify one of these random quantum events, stretching it, feeding it energy, and preventing it from vanishing. It is like a single air bubble forming in molten glass. Under normal pressure, it pops. But if the glass is churned with unimaginable force, that bubble could be captured, inflated, and sealed off, becoming a permanent hollow within the material. In the stellar collapse, that bubble is not made of air but of spacetime itself, pinched off from our own. This process is theorized to occur through something called quantum tunneling, where a system jumps to a new state without passing through the impossible energy barrier in between. The singularity, in its moment of infinite density, could tunnel into an entirely new configuration, birthing a separate cosmic domain. Another compelling idea involves a concept known as false vacuum decay. Think of our universe's fundamental fields as existing in a stable, low-energy state, like a ball resting at the bottom of a deep valley. This is our true vacuum. But some theories suggest there might be other, lower-energy states, like even deeper valleys hidden beneath our feet. The insane energies at a singularity could provide the kick needed to push the quantum fields over a hump, causing them to roll down into a lower energy valley. When this happens, a bubble of this new, true vacuum forms and expands at nearly the speed of light, rewriting the laws of physics within it. This bubble, completely disconnected from our valley, would be a new universe with its own fundamental constants. So the final moments of a singularity child are not just a gravitational collapse, but a quantum lottery of cosmic proportions. The star's death throes provide the energy to magnify a random flicker of quantum foam into a permanent new reality. The birth pangs of a cosmos might be written in the language of probability and uncertainty, a spontaneous eruption of order from chaos, triggered by the most violent death the universe can provide. The mathematics of black holes hold a hidden symmetry, a clue that points toward this astonishing possibility. When Carl Schwarzschild first solved Einstein's equations to describe a non-rotating black hole, he found something peculiar. The solution described a funnel of warped space leading to the singularity, but the math itself did not stop there. It continued, suggesting the existence of a mirrored, parallel space on the other side of that impossible point. This is the theoretical basis for an Einstein-Rosen bridge, what we commonly call a wormhole. For decades, physicists viewed this other side as a mathematical curiosity, a ghost region that was not physically real because the singularity was an impassable barrier. Nothing could cross it and survive. But what if we are looking at it from the wrong perspective? What if the singularity is not a wall in our universe, but a tunnel between universes? The equations hint that the interior of a black hole, as you fall toward the singularity, begins to behave less like a place in space and more like a moment in time. Space itself flows inward like a river over a waterfall, with the singularity acting not as a location you reach, but as a future moment you inevitably hit. This is eerily similar to how cosmologists describe the beginning of our own universe in the Big Bang. In that model, if you run the cosmic film backward, all of space contracts to a single point, a moment in the past that is also not a place but a beginning of time. So mathematically, the interior of a black hole and the early moments of an expanding universe are startlingly similar. They are both described by geometry where space and time swap roles. This profound symmetry suggests the other side of a black hole's singularity might not be a point of destruction in our cosmos at all. It could be the explosive birth of a new one. The wormhole, then, is not a shortcut through our universe. It is a one-way umbilical cord. The funnel of the black hole in our reality is the dying end, while the flaring, expanding geometry on the other side is the living, breathing beginning of a child universe. In this view, every black hole could be a cosmic matryoshka doll. From the outside, we see a dark, silent object, but inside, hidden by the event horizon, an entire new reality may be inflating into existence, forever separated from our own. The star did not die to make a hole, it died to make a door. The search for proof leads us into the realm of the nearly impossible. Detecting a child universe born within a black hole is like trying to hear a whisper from inside a sealed, soundproof vault that is itself locked inside another vault. The event horizon of the black hole acts as the ultimate one-way curtain, severing all direct contact. Any light, any signal, any information from the birth event is trapped forever on the other side, in that new, separate reality. So, if we cannot see the baby universe itself, could we perhaps detect the labor pains? Could the violent act of cosmic birth leave a unique fingerprint on our side of the curtain, imprinted on the dying star's final moments? Theorists suggest a few fragile possibilities, whispers of evidence that hinge on our most advanced and sensitive instruments. The first clue might be written in spacetime ripples. When a singularity child star collapses, it does not simply form a black hole and settle down. The process of a singularity pinching off and inflating into a new cosmos would be a cataclysm of unimaginable violence, a fundamental reconfiguration of geometry itself. Such an event would not produce the clean chirp of two black holes merging that our LIGO detectors have heard. Instead, it might generate a bizarre and complex burst of gravitational waves, a chaotic scream of spacetime that rises to a peak and then cuts off abruptly. The signal would not ring down like a bell as a new black hole does. It would simply stop because the source, the singularity, would have vanished from our universe entirely. Finding such an anomalous signal in the cosmic cacophony would be a monumental challenge, but it would be a potential smoking gun. Another faint whisper could come from Hawking radiation, the theoretical glow that black holes are predicted to emit due to quantum effects. A newborn black hole is incredibly hot and bright in Hawking terms, but it evaporates over eons. However, if the singularity at its heart pinches off into a new universe shortly after formation, it could alter the expected evaporation process. The Hawking radiation might carry a specific, unexpected signature, a subtle anomaly in its energy that hints that the black hole is not quite what it seems, that its core is not a permanent endpoint but a transient portal. Perhaps the most tantalizing possibility lies in the supernova explosion itself. If the core collapse of a massive star leads not to a stable remnant but to a universe-spawning event, the energy balance of the entire explosion could be different. The shockwave that tears the star apart might look unusual, or the distribution of elements forged in the blast could carry a peculiar pattern. Astronomers would need to catch such a rare and brilliant event in exquisite detail, analyzing its light for any sign that a portion of the star's energy and mass did not just collapse but truly vanished from our physics. We are searching for a ghost in the data, for a cosmic magic trick where the magician, the star, disappears without leaving a conventional corpse behind. This hunt pushes our technology and our imagination to their absolute limits, requiring us to look at the most violent events in the cosmos and ask not just how they die, but what they might become. This brings us to a theory that is as elegant as it is radical, a cosmic answer to the question of why our universe is the way it is. The physicist Lee Smolin looked at the puzzle of our finely tuned physical constants and asked a revolutionary question. What if the laws of physics are not fixed, eternal rules, but are themselves subject to a form of evolution? His theory of cosmological natural selection proposes exactly that. It suggests that universes can reproduce, and that the ones we see are the ones best suited for making more of themselves. The mechanism for this cosmic reproduction is the black hole. In Smolin's view, every time a black hole forms in a universe like ours, it gives birth to a new universe in a separate spacetime. This child universe is not an identical copy. Just as biological offspring have slight genetic mutations, the new cosmos inherits the physical laws of its parent, but with tiny, random tweaks. Maybe the strength of gravity is a fraction different, or the mass of an electron is slightly altered. Most of these mutations would be lethal to complex cosmic structure, producing sterile universes that cannot form stars or galaxies. But a few would be advantageous, creating universes that are even more efficient at producing black holes than their parents were. Over countless generations of universes, a form of selection takes place. The universes that win in this cosmic competition are not necessarily the ones most friendly to life. They are the ones most proficient at making black holes. Our universe, with its specific blend of forces that allows for massive stars, supernova, and stellar collapse, might be a champion black hole producer. Its laws are not random gifts, but the result of a deep evolutionary history. In this breathtaking framework, the Singularity Children stars are not just rare anomalies. They are the ultimate agents of this cosmic evolution. They represent the most efficient pathway for a universe to replicate, transforming a dying star not into a dead remnant, but into a fertile seed for an entirely new reality. Each one is a link in an unimaginably vast family tree, a branch point where the laws of physics themselves can diverge and explore new possibilities. We are not living in a random cosmos, but potentially in a highly refined one, shaped by a timeless cycle of stellar death and cosmic birth. The black holes we observe are not endpoints, but promises of new beginnings scattered across the sky. That evolutionary tree of universes leads to a dizzying question about our own place in the grand scheme. If black holes are cosmic nurseries, then every universe is a child of another. So where does that leave us? Could our entire cosmos, with all its hundreds of billions of galaxies, itself be the interior of a black hole born in a grandparent universe? This idea flips our entire perspective inside out. We are not looking out at black holes in our sky, we might be living within one. The theoretical physicist Nikodem Poplawski has explored this very possibility using a model of spacetime that incorporates torsion, a kind of intrinsic twist in the fabric of the cosmos. In his equations, the violent collapse of a massive star in a parent universe does not end at a point of infinite density. Instead, the extreme torsion causes a rebound, an immense bounce that erupts into an expanding new spacetime. From the outside, in that parent universe, observers would see a black hole form. But from the inside, which is our perspective, that bounce is the Big Bang itself. Our entire expanding universe exists beyond the event horizon of that parent black hole, forever hidden from the reality that created it. Think of it like a cosmic Russian doll. Our universe is one layer. The black holes we see inside it are not just objects, they are potentially the seeds for the next layer of dolls within, and our entire doll sits inside a larger one from a previous cycle. This creates a stunning vision of reality, an infinite regress of universes within universes, each born from the gravitational collapse of a star in a parent cosmos. It suggests a cyclical, self-replicating multiverse, a vast and branching fractal of realities. For our own origin story, this means the Big Bang was not a singular, absolute beginning from nothing. It was a transitional phase, a moment of rebirth from a prior state of collapse. The mysterious singularity that marks the start of our cosmic timeline was not a free-floating event, but the specific interior of a black hole in a larger, older reality. This framework could even offer explanations for some of the deepest puzzles in cosmology. The incredible uniformity we see across the cosmos, for instance, might be a result of the smoothing effects of that initial bounce. And the ongoing acceleration of the universe's expansion could be influenced by the torsion from that parent collapse, a kind of inherited spin on reality itself. While this remains a speculative theory, it completes a profound and elegant symmetry. Every star massive enough to become a black hole is a potential universe factory. And if that is true, then we must entertain the breathtaking possibility that we are not just observers of this process, but products of it. We may be living in the aftermath of a stellar death that occurred in a universe we can never see, our entire existence nestled safely inside the ultimate cosmic womb. The final ingredient for a universe might be the strangest matter of all. To understand what could tip a stellar collapse from creating a black hole to birthing a cosmos, we must peer into the heart of matter itself, to a realm far smaller than atoms. Inside every proton and neutron are fundamental particles called quarks, bound together by unimaginably strong forces. In our normal world, quarks are always locked in trios, never found alone. But under the extreme pressures inside a neutron star, something extraordinary might happen. The individual protons and neutrons could be crushed so tightly that their boundaries dissolve, melting into a vast, dense ocean of free quarks. This is a quark-gluon plasma, a state of matter that hasn't existed freely since the first microsecond after the Big Bang, and within this exotic soup, a further transformation is theorized. The quarks we know are called up and down, but there is a third, heavier flavor, the strange quark. Under sufficient pressure, it might become energetically favorable for the up and down quarks to convert into strange quarks. If this happens, the entire stellar core could become a single, gigantic nucleus made of roughly equal parts up, down, and strange quarks. This is a hypothetical object known as a strange star. A strange star would be unlike anything in our current catalogues. It would be staggeringly dense, even more so than a neutron star, and possessed of a perfect iron-like stability. The strange matter at its core is theorized to be the most stable form of matter in the universe, a true ground state. This perfect stability is the key to its potential cosmic role. Imagine a dying star with a strange matter core. As it collapses under its own gravity, it reaches densities where normal neutron star material would give way and form an event horizon. But the strange matter core, in its perfect stability, might resist that final fate just a little longer. It would not bounce or explode, but it could reach a threshold of density and pressure so extreme that it does something even more profound. It could stress the fabric of spacetime to its absolute breaking point, not just warping it into a black hole, but triggering a fundamental phase transition. In this critical moment, the strange star's perfect, uniform density and unique quantum properties might provide the ideal conditions for a singularity to pinch off cleanly. Instead of settling into a permanent endpoint in our universe, the collapse could channel all that immense energy into twisting a knot in spacetime so tight that it snaps, inflating into a new reality. The strange star would not leave behind a corpse for us to find. It would vanish entirely, its entire mass converted into the seed of a new cosmos. In this speculative picture, strange stars are not just exotic stellar curiosities. They could be the perfect cosmic parents, their unique physics making them the most likely engines for universe reproduction. Their formation might be the rare, golden event where matter, energy, and geometry align to turn a stellar death into a cosmic genesis. The violent pinching off of a singularity is only the first moment of a new reality. For that microscopic bubble of spacetime to become a vast, structured cosmos like our own, it needs an engine of explosive growth. This is where one of the greatest modern mysteries of our own universe offers a clue. We call it dark energy, the mysterious force causing our cosmos to expand at an accelerating rate. In the theory of cosmic inflation, a similar but far more powerful form of energy is thought to have existed in the first fraction of a second after the Big Bang. This inflattened field acted like anti-gravity, causing the newborn universe to expand faster than the speed of light, smoothing it out and setting the stage for everything to come. For a child universe born from a stellar collapse, this inflationary kickstart may be absolutely essential. The singularity event itself, that moment of ultimate density and torsion, could be the spark that ignites this field. Think of it like striking a match in a room filled with vapor. The match is the singularity's pinch-off, a tiny, intense event. The vapor is a quantum field latent in the new spacetime, a form of potential energy. The strike triggers a chain reaction, flooding the microscopic bubble with a repulsive force of staggering magnitude. This is the moment the child universe truly becomes independent. The inflattened field, or a primordial form of dark energy, provides the pressure that violently inflates the bubble, stretching it from a quantum speck to a macroscopic domain in an instant. This process does more than just make the universe big. It determines its entire future. The amount of this inflationary energy and how quickly it decays writes the cosmic rulebook. If the inflation is too weak or short, the universe might expand for a moment only to immediately recollapse into a singularity, a stillborn cosmos. If it is too strong or prolonged, the expansion would be so ferocious that matter could never clump together, leaving a forever empty, cold void. The perfect, balanced inflation creates a universe that is flat, smooth, and vast enough for gravity to later form galaxies, stars, and planets. The fate of that universe, whether it expands forever or eventually contracts, is also locked in by these first moments. So the death throes of the singularity child do not just create a new space, they program it. They set the dials for the fundamental forces and determine the ultimate destiny of an entire reality. The star's final act is not merely to give birth, but to provide the initial conditions, the cosmic blueprint, from which an infinity of possibilities may unfold. This leads us to one of the most vexing problems in all of physics, a paradox that threatens the very foundation of our understanding of reality. It is called the black hole information paradox. The universe, according to quantum mechanics, is a meticulous bookkeeper. Information, the specific details that make one particle different from another, can never be truly destroyed. It may be scrambled, but it is always preserved in some form. Yet black holes, as described by classical physics, seem to be the ultimate shredders. Imagine throwing a book into a fire. The book burns to ash, but in principle, a being with perfect knowledge could reconstruct the book from the precise pattern of smoke, heat, and light emitted. The information is transformed, not lost. Now, throw that same book into a black hole. According to Hawking's work, a black hole slowly evaporates over eons, emitting only a faint, featureless glow of thermal radiation. This radiation, in theory, carries no information about what fell in. It is just random heat. When the black hole finally vanishes, all the unique information about that book, every word on every page, seems to have been erased from the universe. This is the paradox. The flawless accounting of quantum mechanics clashes violently with the apparent destructive power of gravity. For decades, physicists have wrestled with this, seeking a way to preserve the information. The Singularity Children model offers a radical and elegant escape clause. What if the information is not lost at all, but simply relocated? In this solution, the information of everything that ever falls into the black hole, from interstellar dust to entire stars, does not get trapped at the singularity or radiated away as meaningless noise. Instead, it passes through the singularity, becoming the foundational data, the initial conditions for the child universe. The singularity acts not as a shredder, but as a cosmic printer head, encoding all that information onto the fabric of the new reality as it inflates. The book you threw in is not destroyed. Its information becomes woven into the fundamental quantum fields of the new cosmos, perhaps influencing the pattern of its first density fluctuations, the seeds of its future galaxies. In this view, our own universe's specific structure, the arrangement of galaxy clusters we see today, might carry subtle imprints of the material that fell into our parent black hole in a long-vanished cosmos. This solves the paradox by changing the scale of the ledger. Information is not lost within our universe because it is transferred to a new accounting system, a separate reality with its own spacetime. The black hole's event horizon is not a point of no return for information, but a one-way data port. This transforms our understanding of a black hole's purpose. It is not a cosmic trash compactor. It is a compiler gathering the experiences of one reality and using them to write the opening lines of another. The fate of what falls in is not oblivion, but reincarnation on a cosmic scale. Every atom, every bit of light, every complex structure swallowed contributes to the blueprint of a new beginning. The timeline of this cosmic birth is both unimaginably brief and unfathomably long. It begins with the final, desperate heartbeat of a star that has lived for millions of years. Deep within its core, the last embers of nuclear fusion flicker and die. For eons, the outward push of radiation has battled the inward crush of gravity. Now, gravity wins. In less than a single second, the star's core, a sphere thousands of miles across, collapses inward. It shrinks from the size of a planet to the size of a city, to a mountain, to a building. Matter is compressed beyond all recognition. Protons and electrons are forced together, merging into neutrons. The core becomes a seething ball of nuclear fluid, a proto-neutron star still shrinking. But if this star is a singularity child, the collapse does not stop here. The pressures become so extreme that even neutrons cannot hold their form. They dissolve into a quark-gluon sea, and perhaps into the perfect, strange matter that provides the final, critical stability. The collapse accelerates, rushing toward its ultimate destiny. This is the moment the star vanishes from our observable universe. An event horizon forms, a point of no return for light and information. But inside that dark shroud, the drama is just reaching its climax. The core continues its headlong rush toward infinite density. This is the formation of the gravitational singularity. In our universe, this is where the story ends. In this model, it is where a new story begins. The singularity is not a static point. It is a dynamic, twisting knot in the fabric of spacetime, stressed to its absolute limit by the torsion of the collapse. Then, in a span of time so short it has no classical meaning, a quantum event occurs. A fluctuation in the seething quantum foam at the Planck scale is caught and magnified by the insane energies. The singularity undergoes a quantum bounce. It pinches off. Think of it like a droplet of water forming on a faucet. The droplet stretches, connected by a thin thread, and then it separates completely, falling away. In that instant of separation, the connection to our parent universe is severed. The pinched-off singularity is no longer part of our reality. It is a seed. And with that pinch, a new clock starts ticking, time zero for a new cosmos. The first fraction of a second after the pinch-off is the most important epoch in the life of this baby universe. The energy of the stellar collapse now contained within that seed ignites. A primordial field, something akin to the inflattened field, is activated. This field floods the microscopic bubble with a repulsive force of staggering power. Inflation begins. The universe expands faster than the speed of light, doubling in size repeatedly over intervals as brief as 10 to the negative 37 seconds. In less time than it takes for light to cross a single proton, the universe grows from a quantum speck to a macroscopic domain larger than our entire observable universe today. This violent stretching does two crucial things. It smooths out any initial irregularities, creating the stunning uniformity we see in our own cosmos. And it imprints quantum fluctuations from that first moment onto the fabric of space itself, stretching them into vast ripples that will later, under gravity, become the seeds for galaxies and galaxy clusters. After this explosive inflation, the field decays. Its energy is converted into a hot, dense soup of fundamental particles and radiation. The universe is now a blazing fireball, a cosmic plasma. This is the hot Big Bang phase of the child universe. From here, the familiar cosmic story unfolds, but written with the unique laws inherited from its stellar parent. Particles form, nuclei fuse, atoms coalesce as space cools and expands over hundreds of thousands of years. Gravity slowly works on those imprinted ripples, pulling matter together over millions and billions of years to form the first stars, the first galaxies, and eventually, perhaps, the first planets. What began as the catastrophic death rattle of a star in another reality has, through this astonishing chain of events, become the dawn of an entirely new cosmic day, complete with the potential for its own stars, its own black holes, and its own future generations of singularity children. The diversity of these stellar offspring would be staggering, a true zoo of cosmic possibilities. Each child universe, born from the unique quantum chaos of a different stellar collapse, could be a realm of unrecognizable physics. The fundamental dials of reality, what we call the constants of nature, would be set to new values in that first explosive moment. In our universe, these constants appear finely tuned. The strength of gravity, the charge of an electron, the speed of light, these numbers are not derived from a deeper theory, they are simply measured. And they seem perfectly balanced to allow for atoms, stars, planets, and life. But in a child universe, that balance could be shattered. Imagine a cosmos where the strong nuclear force, which binds atomic nuclei together, is slightly weaker. In such a place, protons and neutrons could never stick together. Hydrogen would be the only element, and stars as we know them could never ignite. The universe would be a dark, eternal sea of simple gas, forever sterile. Conversely, if gravity were significantly stronger, the universe would be brutally short-lived. Matter would clump together with such ferocity that the entire cosmos might collapse back into a singularity almost immediately after its birth, a fleeting cosmic sigh. But not all differences would be catastrophic. Some universes might be merely strange. Consider dimensionality. We experience 3 dimensions of space and 1 of time. But the mathematics of string theory and other models suggest other configurations are possible. What would a universe with 4 spatial dimensions be like? In such a place, gravity would obey a different law, falling off more rapidly with distance. Solar systems as stable as ours might be impossible, but entirely new forms of celestial architecture could arise, structures we cannot even visualize. Life, if it emerged, would perceive and interact with a reality of hypercubes and impossible knots, a geometry beyond our comprehension. The very fabric of spacetime could differ. Some child universes might be born with a different number of fundamental forces. Perhaps in one, the electromagnetic and weak nuclear forces never separated, remaining fused into a single electroweak force even at low energies. Chemistry in that universe would be utterly alien, with atoms bonding in ways that are nonsensical to our periodic table. Light itself might behave differently, with photons having mass or traveling at a speed that is not the universal speed limit. The possibilities extend to the very large and the very small. One universe might have a cosmological constant, our dark energy, that is 1,000,000,000 times stronger, causing it to inflate and dilute into emptiness before the first star could ever form. Another might have one that is negative, causing a global collapse from the very beginning, a universe born with a death sentence. Yet another might have conditions that make something like cosmic strings or magnetic monopoles common, threading the cosmos with bizarre defects that shape galaxy formation. This incredible variety stems from the quantum fluctuations that are amplified during the universe's inflationary birth. In our universe, one specific set of random quantum bumps was stretched to cosmic scales, becoming the blueprint for our web of galaxies. In the child universe next door, born from a different star, a different random set of fluctuations was captured and inflated. That unique quantum fingerprint dictates everything from the distribution of its first matter to the eventual complexity it can foster. So the multiverse spawned by Singularity Children would not be a collection of similar universes. It would be a vast, branching tree of experimentation where the laws of physics themselves are the variables. Most branches would be dead ends, cosmic stillbirths, or eternal voids, but a rare few, through sheer chance, would land on a stable, fruitful set of laws, allowing for structure, complexity, and perhaps even observers to one day gaze up at their own night sky and wonder if they too are living inside a black hole. This random cosmic lottery forces us to confront a profound and ancient question. Why does our universe seem so perfectly suited for us? The strength of gravity, the charge of the electron, the energy in empty space, these numbers are not just arbitrary. If they were even slightly different, atoms would not hold together, stars would never ignite, and life as we know it would be impossible. This is the puzzle of fine-tuning, a mystery that has long pointed toward either incredible cosmic luck or some form of intentional design. But the theory of Singularity Children offers a third, deeply compelling answer, one rooted in a simple, observational truth. We call this the anthropic principle, revisited through a cosmic lens. It states quite simply that we can only observe a universe that is capable of producing observers. If a cosmos cannot form stars, planets, and conscious beings, then there is no one there to ask why it is the way it is. In a static, single universe, this feels like a tautology, a circular argument. But in a multiverse spawned by stellar collapses, it becomes a powerful statistical inevitability. Imagine a vast, endless field of puddles after a rainstorm. Each puddle is a separate universe with its own unique shape and depth. Now, imagine a fish wondering why the water in its puddle is just the right depth for it to swim. The fish cannot wonder about the puddles that dried up instantly or the ones that are only a millimeter deep. It can only exist and therefore ask the question from within a puddle that has the right conditions for fish. The fish's existence automatically selects for the puddle that can support it. Our situation is precisely the same, but on a cosmic scale. If an infinite number of universes are being born from dying stars, each with randomly set physical constants, then the vast, overwhelming majority will be stillborn or sterile. They will collapse immediately, expand into empty voids, or have laws that prevent any complex structure from ever forming. But by pure chance, a tiny fraction will land on a stable, fruitful set of laws, one that allows for galaxies, stars, planets, and eventually, curious minds to look up at the night sky. We are not the lucky winners of a 1 in a trillion cosmic lottery held in a single universe. We are the inevitable inhabitants of one of the rare universes that work. Our finely tuned constants are not a sign of special creation, but a consequence of our own existence as observers. We had to find ourselves here because this is the only kind of place where beings like us could ever arise to ponder the question. This framework transforms the fine-tuning problem from a philosophical shock into a natural prediction of a self-replicating cosmos. The laws we see are not fine-tuned for life in general. They are fine-tuned for the creation of black holes, which are the engines of cosmic reproduction. And it just so happens that the same conditions that make a universe prolific at creating black holes, stable stars, and dense stellar remnants also create the environments where life can eventually emerge. So when we measure the precise strength of the forces that bind our reality, we are not reading a divine blueprint. We are reading the user manual for a universe that is exceptionally good at making more of itself. Our very ability to do the measuring is proof that the manual works. The grandeur of this cosmic vision cannot hide a fundamental and necessary question. Is this even science? The idea of stars birthing universes is undeniably beautiful and philosophically profound, but it currently sits in a precarious space at the very edge of theoretical physics. For many in the scientific community, this is not a flaw in the theory, but its defining characteristic. The core criticism is one of falsifiability. A cornerstone of the scientific method is the ability to test a hypothesis, to make predictions that can be proven wrong by observation or experiment. If a theory cannot, in principle, be falsified, it risks drifting into the realm of metaphysics or pure philosophy. And how do you test for something happening inside an event horizon in a separate spacetime with different laws? The evidence we discussed, like anomalous gravitational wave signals or strange supernova signatures, are fragile whispers at best. Detecting them would be monumental, but their absence would not disprove the theory. It would simply mean we haven't seen it yet. This is the challenge. The theory is constructed to explain phenomena that are, by their proposed nature, permanently hidden from our view. We are asked to believe in cosmic reproduction based on the behavior of things we can never directly observe. Critics argue this makes it less a scientific theory and more a compelling narrative, a story that connects the dots of black holes and the Big Bang in an elegant but ultimately untouchable way. They point out that invoking an infinite multiverse of unseen realms can be used to explain anything, and therefore explains nothing in a scientifically useful sense. Yet, to dismiss it entirely is to misunderstand the history of science. Some of our most successful theories began as untestable speculations. The concept of continental drift was mocked for decades before plate tectonics provided the mechanism. The idea of atoms was philosophical for centuries before technology caught up. The role of these bold, boundary-pushing ideas is not to provide immediate answers, but to expand the landscape of the possible. They force us to re-examine our assumptions, to ask if our current tools are sufficient, and to dream of new ones. The Singularity Children hypothesis does precisely this. It takes the known paradoxes of black holes and the mystery of our universe's origin and proposes a radical synthesis that, while currently untestable, is mathematically coherent within certain extensions of general relativity and quantum mechanics. It is a stress test for our understanding, showing where our equations break down and hinting at what might lie beyond. This is the cutting edge, not of confirmed discovery, but of guided imagination. It represents a phase of science where speculation is necessary to illuminate the path forward. The value lies not in proving we live inside a black hole, but in using that idea to ask better questions. What unique signatures would a universe-spawning collapse leave? How could we design an experiment or an observation to constrain these possibilities? By stretching our concepts of reality to their limits, we define the frontier, and history suggests that today's philosophical speculation has a curious habit of becoming tomorrow's testable physics. The search for proof leads us to listen for a sound that has never been heard. Gravitational waves, the ripples in spacetime itself, offer our most promising ear to the cosmos. We have already heard the chirps of black holes merging and the thuds of neutron stars colliding. These signals match the predictions of Einstein's equations beautifully. But the birth of a universe would not sound like a merger. It would be a scream and then a sudden, profound silence. Theorists suggest the waveform from a universe spawning event would be utterly unique. Imagine the signal from a collapsing star. It would rise in frequency and amplitude as the core implodes, a crescendo of warping space-time. But instead of that signal ending with the characteristic ring down of a newly formed black hole, where the waves fade away like a struck bell, it would simply cut off. Abruptly, the moment the singularity pinches off and detaches into a new reality, the source of the gravitational waves in our universe vanishes. The signal would not have a tail. It would be a sharp, catastrophic spike that ends not with a fade but with a cliff. Our current detectors like LIGO and Virgo are tuned for the frequencies produced by stellar mass events, collisions that happen in a fraction of a second. A universe-spawning collapse from a primordial star might be too brief, too violent, and too rare for these instruments to easily catch. But the future of gravitational wave astronomy holds incredible promise. Space-based observatories like the proposed LISA mission, a constellation of satellites, would listen to a much lower frequency band. Here, in the millihertz range, we could hear the mergers of supermassive black holes, events that shake space-time for months or even years. Could such an observatory hear the birth of a universe? Perhaps. The inflationary expansion of that new cosmos, happening just on the other side of the pinch, might impart a final, unique jolt to the surrounding space-time of the parent black hole. This could leave a distinctive fingerprint on the very low-frequency gravitational waves, a kind of aftershock signature imprinted on the event horizon itself. Detecting this would be like trying to hear the pop of a soap bubble forming from inside a sealed room by listening for the faintest vibration in the wall. It pushes our sensitivity to the absolute limit. The hunt, then, is for the anomalous signal, the one that does not fit the clean templates of known collisions. It is a search for the cosmic outlier, the scream that ends not with a whimper, but with the silence of a door closing between realities. This profound silence in the cosmos is not just a technical challenge, it is a philosophical one. It brings us face to face with the haunting question posed by physicist Enrico Fermi. If the universe is so vast and old, and the ingredients for life seem common, where is everybody? The persistent lack of any signal, any artifact, any evidence of other civilizations is known as the Great Silence. The theory of Singularity Children offers a startling new lens to view this paradox. If our universe is not a random, eternal expanse, but a specific child born from a specific stellar collapse, then it has a concrete and finite age. We know that age, roughly 13.8 billion years. That may seem like an incomprehensibly long time, but in the context of cosmic evolution, it might be the blink of an eye. What if that simply is not enough time? The journey from the first stars to intelligent, technology-building civilizations could be a marathon, not a sprint. Consider the timeline on Earth alone. Our planet formed about 4.5 billion years ago. Single-celled life emerged relatively quickly, but it took over 3 billion more years for complex, multicellular life to appear. The leap to tool-using, language-having, civilization-building intelligence is an even rarer and more recent event, occupying just a sliver of the last 100,000 years. If this arduous, fragile sequence is even remotely typical, then the window for intelligent life to arise in any given universe might be exceedingly narrow, requiring many billions of years of stable, uninterrupted planetary evolution. In a cosmos that is only 13.8 billion years old, we may be among the very first, if not the first, to reach this stage. We are not latecomers to a crowded galactic party. We might be the earliest arrivals, sitting in a quiet, empty hall, waiting for others to show up. This shifts the meaning of the silence entirely. It is not evidence of our loneliness or the impossibility of others. It could be a sign of our cosmic youth. We are living in a universe that is still fresh, still fertile, still in the early chapters of its story. the first generations of stars had to live and die to forge the heavy elements needed for planets like Earth. Those planets then needed billions of years of stable conditions for life to experiment, evolve, and eventually look up at the stars. In this view, the Great Silence is not a wall but a horizon. We are looking out across a landscape where the seeds of intelligence have only just been sown. Other civilizations may be out there, still in their planetary infancy, their oceans teeming with simple life that has yet to invent the radio telescope. Or they may be just on the cusp, their first signals still centuries or millennia away from reaching us. The silence is profound, but it may be temporary. This idea connects deeply to the concept of cosmic evolution through black holes. If a universe needs to be old and stable enough to produce intelligent life that can eventually look back and understand its origins, then perhaps the most successful, long-lived universes are not just good at making black holes, but also at fostering the rare conditions for consciousness to emerge. We are not just products of a universe tuned for reproduction. We may be the universe becoming aware of itself, the first faint glimmer of a cosmic mind awakening in a young and still silent reality. We cannot see a universe being born, but we can try to build one in thought. When direct observation is forever out of reach, science turns to its most powerful tools, the abstract languages of mathematics and computation. To study the genesis of a child universe, physicists construct elaborate thought experiments and digital worlds, using the rules of logic to explore realms beyond our telescopes. This begins with the equations of general relativity, which describe how mass and energy warp the fabric of spacetime. By pushing these equations to their breaking point at the singularity, mathematicians can explore what geometries are possible when that fabric tears and reconnects. They model the pinch-off of a singularity not as a destruction, but as a topological change, a reconfiguration of the very connectivity of space. Think of it like modeling the moment a soap bubble separates from the wand. We cannot see the exact molecular transition, but the mathematics of surface tension and fluid dynamics can describe the forces that make it possible and predict the new, stable form that results. In these models, the black hole's interior geometry is stretched and twisted until it forms a neck, a wormhole-like structure that narrows to a point and then pinches closed. On one side of that pinch is our universe. On the other side, the equations show an expanding, flaring geometry that looks mathematically identical to the start of an inflationary Big Bang. The numbers tell a story of a bridge becoming a beginning. To give these equations life, researchers turn to the immense power of supercomputers. They cannot simulate an entire star collapsing into a new cosmos, but they can create simplified digital models that capture the essential physics of spacetime under extreme stress. These simulations test how a region of warped geometry might behave when infused with the theoretical energy fields that drive cosmic inflation. Does it stabilize and expand, or does it collapse back in on itself? The simulations act as digital laboratories, running thousands of virtual experiments with slightly different starting conditions. They ask what combination of torsion, density, and quantum field values leads to a persistent, growing universe rather than a fleeting fluctuation. It is a process of cosmic trial and error, conducted at the speed of silicon, hunting for the mathematical pathways that make Genesis plausible. In a fascinating parallel, some of the most promising insights come not from astrophysics, but from the study of materials here on Earth. The field of condensed matter physics examines exotic phases of matter, like superconductors and superfluids, where collective behaviors of billions of atoms give rise to entirely new phenomena. Remarkably, the mathematics describing disruptions in these materials, like vortices in a superfluid or defects in a crystal, can be eerily similar to the equations describing topological defects in spacetime itself. A team might study how a vortex forms in ultra-cold helium, not to understand helium, but because the mathematical structure of that event is an analog for how a wormhole throat might form or how a singularity could pinch off. The laboratory becomes a metaphor, a physically tangible hint about processes that are otherwise unimaginable. One of the most startling examples of this is the creation of simulated wormholes on quantum computers. In a landmark experiment, researchers used Google's Sycamore processor to model a holographic wormhole. They did not create a tunnel in space, of course. Instead, they mapped the complex quantum physics of a wormhole's traversal onto the interactions of entangled qubits in their machine. By watching information travel between the qubits in a way that mirrored how it might pass through a wormhole, they tested the quantum mechanical behavior of these hypothetical bridges. While this was a vastly simplified model, it demonstrated a profound principle that the mysterious connection between quantum entanglement and spacetime geometry can be probed with our most advanced tools. These analog systems and simulations are the closest we can come to a laboratory test of cosmic birth. They allow us to ask, if the laws of physics allow for a child universe, what would that process look like in its earliest moments? What energies would be required? What signatures might briefly flash into existence in our reality before the final pinch? Each simulation is a question posed to the universe, a sketch of a possibility. They remind us that even the most untouchable ideas must still obey the rigid, unforgiving logic of mathematics. If the numbers do not add up, the idea, no matter how beautiful, must be revised or abandoned. This rigorous, indirect exploration is how we chart the invisible, building maps of potential realities, one equation, one simulation, and one clever analogy at a time. This perspective weaves our existence into a story of cosmic inheritance. If our universe is a child, then every atom in our bodies carries a profound lineage. The carbon in our cells, the oxygen in our lungs, the iron in our blood, these were not forged in the first moments of our cosmos. They were cooked in the hearts of stars that lived and died long after our universe began. But the stage for those stars, the very laws of physics that allowed them to shine, may have been set by a stellar ancestor in another reality. We are, in a literal and breathtaking sense, the descendants of stars twice over. First, through the biological stardust that makes our physical forms, and second, through the cosmic architecture that made those forms possible, an architecture potentially born from a stellar collapse. This reshapes our identity from accidental inhabitants of a random cosmos to conscious expressions of a grand, generative process. We are not just living in a universe, we are the outcome of its stellar ancestry. It blends rigorous science with a deep, almost mythic sense of genealogy. For millennia, human cultures have told stories of our origins, linking ourselves to the earth, the sky, or divine creators. Modern science gave us a new story, one of cosmic expansion and stellar nucleosynthesis. The Singularity Children theory offers a bridge between these narratives, adding a layer of cosmic parenthood. It suggests a family tree whose roots are not in a garden, but in the furnace of a dying star. Our cosmic parent may be nameless and forever lost to us, but its legacy is everything we see and are. This connection ties us directly to the most violent and creative forces in existence. The same process that seeds new universes, the gravitational collapse of massive stars, also creates the heavy elements essential for planets and life. The stellar death that might birth a cosmos is the very same process that, generations later within that cosmos, forges the building blocks of beings who can ponder their own origins. We are connected to that generative violence not just as beneficiaries but as heirs. This realization carries a quiet, humbling weight. It means the night sky is not a distant, indifferent panorama. It is a family portrait. Every black hole we cannot see, every remnant of a massive star, is a potential sibling or a cousin to our own cosmos, a testament to the same generative cycle that brought our reality into being. When we look at the Orion Nebula, a stellar nursery where new stars are being born, we are not just looking at the future. we might be looking at a reflection of our own cosmic past, a glimpse of the kind of place where our universe's parent star once lived. Our search for understanding becomes a form of cosmic self-discovery, an attempt to learn about our own lineage by studying the rules of our home. The laws of physics we are meticulously measuring are not just abstract rules, they are our inheritance, the unique constants passed down from a stellar event we can never witness. This transforms our scientific curiosity into something more personal. We are not just mapping the universe, we are reading our own cosmic birth certificate, trying to decipher the faded handwriting of a parent we will never meet. The silent cosmos is not our final answer, only a challenge to our ingenuity. To hear the birth of a universe or see the imprint of a parent cosmos, we must build tools that listen and look in ways we have not yet conceived. The next generation of observatories will not just be bigger versions of what we have today, they will be entirely new senses for humanity. Space itself will become our laboratory. The Laser Interferometer Space Antenna, or LISA, is a mission that will transform our ability to hear the cosmos. Instead of detectors on Earth, it will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by laser beams. This floating observatory will listen to the low-frequency rumble of the universe, a gravitational wave band where the collisions of supermassive black holes play out over years. It is within this deep, resonant hum that theorists hope to find anomalies, the subtle, unexpected signatures that could betray a universe-spawning event. Perhaps the ring-down of a merging black hole will have a strange echo, or a collapse signal will end with a frequency spike that current theory cannot explain. LIS as exquisite sensitivity could catch the gravitational aftershock of a singularity pinching off, a last tremor in spacetime before the connection to a child universe is severed. On the electromagnetic side, the Vera-C, Rubin Observatory will soon begin a 10-year survey of the entire southern sky, not just taking pictures but making a cosmic movie. It will detect billions of galaxies and millions of supernovae. Its immense data stream will be scoured by artificial intelligence for the ultimate outlier, the supernova that does not behave like any other. Could it find an explosion where the light curve, the brightening and fading of the star, suggests the core did not simply form a neutron star or black hole, but vanished in a way that defies our models? Finding even one such event would send shockwaves through astrophysics. Further ahead, we dream of quantum gravity probes. These are not telescopes in any traditional sense. They are experiments that attempt to measure the fabric of spacetime at its smallest possible scale, the Planck length. One concept involves using incredibly precise atomic clocks or quantum-entangled particles in space to detect minute fluctuations in the passage of time or the geometry of space itself. If the vacuum of space is truly a seething quantum foam, as theory suggests, and if black holes or cosmic events can disturb that foam in detectable ways, such a probe might one day sense the residual vibrations from a nearby cosmic birth, like feeling the distant rumble of an earthquake through the ground long after it has passed. The ultimate indirect evidence might be written in the oldest light we can see, the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang fireball, and it contains incredibly subtle patterns, tiny variations in temperature. Future satellites, even more sensitive than the Planck Observatory, could map these patterns in exquisite detail, searching for signatures that our universe underwent not just one inflation, but experienced a kind of inheritance. Some models suggest that if our universe was born from a black hole in a parent cosmos, the specific way our inflation started might leave a faint circular pattern or a specific type of polarization in this background radiation. It would be a cosmic fingerprint, a birthmark from our parent star, imprinted on the sky 13.8 billion years ago and waiting for us to develop the eyes to see it. And then there are the technologies of pure imagination. Could we ever create a laboratory-scale analog of a universe, Some physicists speculate about using ultra-intense lasers or collisions in particle accelerators to create conditions so dense and energetic that they momentarily mimic a tiny patch of the early universe. While this would not create a true, expanding cosmos, it could allow us to study the physics of phase transitions in spacetime, watching how a false vacuum might decay or how a quantum bubble might form. Each of these missions, from the near future to the speculative, represents a step toward answering a question that currently lies in the realm of mathematics and philosophy. They are our attempts to build a key for a door we are not even sure exists. The quest is not for a direct photograph of a child universe, but for the shadow it casts, the echo it leaves, the subtle crack in the wall of our reality that says, something extraordinary happened here. We are building the tools to listen for a story written in gravity, light, and the quantum whisper of empty space. Every great mystery invites more than one possible solution. The notion of stars birthing universes is not the only radical idea trying to explain our cosmic origins. It exists within a vibrant constellation of competing theories, each painting a different picture of reality's ultimate structure. To see where the Singularity Children hypothesis fits, we must place it alongside its peers on the cutting edge of cosmology. One of the oldest and most elegant alternatives is the cyclic universe model. This idea proposes that the cosmos undergoes an endless series of expansions and contractions, a perpetual cosmic heartbeat. In this view, the Big Bang was not a unique beginning from nothing, but the latest rebound from a previous collapse, a big bounce. Here, there is a clear point of agreement with our stellar genesis story. Both models replace a singular, absolute beginning with a transitional event, a moment where an older state gives way to a new one. The critical difference lies in the scale and mechanism. In the cyclic model, the entire universe collapses and rebounds as one entity. In the Singularity Children model, reproduction happens locally through individual stellar collapses within a larger, possibly eternal, parent cosmos. One is a global pulse, the other a process of cosmic budding. The cyclic universe is a closed loop, while the stellar birth idea suggests an open-ended, branching tree of realities. Then we have the vast edifice of string theory and its associated concept of the multiverse, often called the string theory landscape. This framework suggests our universe is just one bubble in a frothing cosmic foam of perhaps 10 to the 500 different possible universes, each with different physical laws. The Singularity Children hypothesis fits neatly as a potential mechanism for generating that landscape. String theory describes the possibilities, the vast menu of physical constants. But how are those possibilities actually realized? How does a specific universe with a specific set of laws come into being? The collapse of a special star could be the engine that selects one point on that landscape and brings it to life. In this synthesis, the dying star is the needle that stitches a new bubble of reality from the quantum fabric, its unique collapse determining which set of string theory's vibrational patterns define the new cosmos's laws. So rather than competing, these ideas can be complementary, one providing the catalog of possibilities, the other providing the creative act that instantiates them. A more profound and mind-bending competitor is the holographic principle. This theory, born from the study of black hole thermodynamics, suggests that all the information describing a three-dimensional volume of space can be encoded on a two-dimensional surface surrounding it, like a cosmic DVD. In its most extreme form, it proposes that our entire three-dimensional universe is a holographic projection from information stored on a distant two-dimensional boundary. At first glance, this seems to clash with the Singularity Children idea. One is about projection from a boundary, the other about birthing new volumes from a point. Yet, they intersect beautifully at the event horizon of a black hole. The holographic principle tells us that everything that falls into a black hole is not lost, but its information is smeared and encoded on the horizon surface. The Singularity Children model then offers a destiny for that information. It is not stored forever on a static surface, but transferred through the singularity to become the initial data for a new universe. The black hole's horizon is the encoder, and the pinching singularity is the projector, casting that information into a brand new three-dimensional reality. In this way, the holographic principle could describe the preservation mechanism, while the stellar birth describes the reproductive outcome. Finally, we have the steady-state theory, an older model largely abandoned due to the discovery of the cosmic microwave background. It proposed a universe with no beginning or end, constantly creating new matter to maintain a constant density as it expands. The Singularity Children idea is, in a sense, a modern, localized successor to this philosophical preference for a universe without a singular creation event. Instead of continuous matter creation everywhere, it proposes sporadic universe creation in specific, extreme locations, black holes. It replaces an eternally unchanging cosmos with an eternally reproducing multiverse, achieving a similar goal of avoiding a definitive beginning, but through a dynamic, evolutionary process rather than a steady state. So where does this leave our stellar genesis story? It is not a lone voice crying in the dark. It is a provocative thread woven into a larger tapestry of speculative cosmology. It agrees with others in seeking to move beyond a one-time Big Bang. It finds potential harmony with string theory's landscape and the holographic principle's information coding. It offers a specific physical mechanism where others offer abstract mathematics. Its greatest strength may also be its point of contention. It grounds the awe-inspiring concept of cosmic creation in the familiar, observed astrophysics of stellar collapse, suggesting that the engines of Genesis are not hidden in a metaphysical realm, but are shining and dying in our skies right now. The competition between these ideas is not a conflict to be won, but a conversation that defines the frontier. Each theory pushes the others to be more precise, to explain more, to connect better with the faint signals we detect from the edge of understanding. In this grand dialogue, the story of Singularity Children adds a compelling, tangible question to the mix. We no longer just ask what banged or why it banged. We ask, what if our cosmos was not the first bang, but the latest in an endless chain of stellar echoes? The most staggering implication of all is not about our past, but about our future. If the universe can reproduce through stellar collapse, could that process ever be guided or even initiated by intelligence? Could a civilization, having unraveled the deepest laws of physics, learn to build a universe of its own? This is the realm of cosmic engineering, a concept that blurs the line between ultimate science and profound creation. The scale of such a project is, of course, beyond anything we can currently conceive. To birth a cosmos, you would need to recreate the conditions at the heart of a dying singularity child star. That means concentrating an amount of energy and mass equivalent to many stars into a volume smaller than an atom, and then triggering a controlled quantum bounce that pinches off a new spacetime. The energy requirement alone is incomprehensible. A single star's entire lifetime output released in a final cataclysm might be just enough fuel for one Genesis event. An advanced civilization might harness the power of entire galaxies, perhaps by building a Dyson sphere around not one star, but millions, or by directly tapping the rotational energy of a supermassive black hole. They would need to manipulate matter at the Planck scale, the domain where gravity and quantum mechanics merge, commanding forces that twist the fabric of reality itself. The technology required would be indistinguishable from magic, a mastery over the fundamental architecture of existence. But let us assume for a moment that such a feat becomes possible. The ethical and philosophical questions it raises are as vast as the cosmos one would create. What responsibility does a creator have to its creation? Would the new universe be a sterile experiment, a work of art, or a sanctuary for life? Would the engineers program the laws of physics to be hospitable, or would they allow for random variation, embracing the chaos of natural cosmic evolution? There is a haunting consideration here. If our universe is a product of such engineering, then our own physical laws might reflect the intentions or perhaps the aesthetic preferences of our cosmic parents. Our fine-tuning could be a signature of design, not blind evolution. Conversely, if we were to create a universe, we would become the mysterious progenitors in someone else's origin story. The beings that might one day evolve in that child cosmos would look back at their Big Bang and see only a natural, spontaneous event, never knowing it was an act of deliberate creation from a reality they can never access. This circles back to our own search for meaning, our drive to understand the cosmos, to push the boundaries of physics and energy, might itself be a nascent form of this ultimate creative impulse. We are already cosmic engineers in miniature, altering our planet and reaching for the stars. Could that ambition, given enough time and knowledge, mature into the ability to spark a new reality, to become not just children of the stars but parents of universes? The journey we have traced is one of breathtaking transformation, from the cataclysmic death of a single star to the silent dawn of an entire cosmos. It begins with a collapse, a point of infinite density where our physics fails, and asks us to see not an end but a bridge. The speculative leap is that this singularity, this terrifying finality, can pinch off, inflate, and become the seed for a new reality with its own space, time, and physical laws. We have followed the trail from the mathematics of black holes to the quantum foam, from the fine-tuning of our universe to the eerie silence of the cosmos, all through the lens of stars that might be cosmic parents. This idea of singularity children, while firmly in the realm of theoretical possibility, does something essential. It challenges the very framework of our understanding, forcing us to reconsider the life cycle of stars, the nature of black holes, and the origin of everything we see. It replaces a static, one-time beginning with a dynamic, generative process, weaving our existence into a vast, possibly infinite family tree of universes. The evidence remains elusive, hidden behind event horizons and encoded in quantum whispers, but the pursuit itself expands the horizon of what we believe is possible. It teaches us that the most profound mysteries often lie at the intersection of our greatest knowledge and our deepest ignorance. So tonight, when you look up at the night sky, see it anew. Those points of light are not just distant suns. Some of them, in their final, magnificent fury, might be cradles. Within their hearts, in a moment of unimaginable violence, the fabric of our reality might be twisting into a doorway, and on the other side, a new infinity is taking its first breath. Let that wonder pull you forward. Stay curious, keep questioning, and remember that the universe's greatest story may be one it is still writing, one stellar genesis